All right, so we are almost ready to get started. We only got like 2 people on the Discord screen share session right now, so very few people are gonna hear what I'm gonna say now, which is nothing, because I'm gonna wait until most people are on in order to say what I need to say. Live stream is on already, and let me see whether people have realized. Oh, I haven't posted the link. Well, that part really is not needed because once people know how to find my channel, um, they can actually just find it, right? And I guess people have not figured that part out yet. They're still waiting for my link to get into live stream, even though everything is public. Okay, so we'll go ahead and do that. There we go. All right, so I just have to say something about what Mohammed wrote. He felt like he's playing against the house. Well, but the thing is, there's no gambling involved here. There's nothing that should be left to chance. I mean, that's kind of how I see it. Is there's really nothing left to chance when you're taking a class in CIS. I mean, it's the material is already all here. Yep, I forgot to screen share on Discord, so let me go ahead and do that. There we go. All right, much better. Now that we have most people either on. All right, so we got 9 people on YouTube, and I'm just doing a rough quick count here, and we got about 10-ish on Discord. So let's just call this 20 people. That's about 1/2 of the class. Yep. So I'm not. Um, well, I'm not gonna say it. I would only say that the intention of using synchronous session for this class is to encourage people to be in the lecture so that they will be interacting. So when I present something and they have questions, they can ask questions right away, and I can respond to those questions right away, and so on. And the other thing is to kind of try to get people into a structure. So on Tuesdays and Thursdays at starting at 5:30 p.m. We do a certain thing, and then maybe shortly before, there's a little study session, a little review of what we have gone through and talked about already. Kind of go through some of the questions that you guys might have, when you're doing your assignment or your lab, or when you're studying the material. So that's sort of my original intention of having a synchronous class instead of asynchronous class. As it turns out, actually, it was surprising to me that I was one of very few professors actually using the synchronous mode instead of the asynchronous mode of teaching online classes. So that part kind of surprised me a little bit because I really don't know how people can teach classes like this in an asynchronous mode. I really don't. I mean, yeah. Anyway. All right. So let's see. It is time already. We're 2 minutes past. Okay. So any questions about the lab/homework? I say lab/homework because one portion of it is due at the end of the day of the lecture, and then the other part is due in a week. So I think some people were probably thinking, "Oh, I got time to do this," and my response is, "No, you actually do not," because this kind of program, especially if you do this the first time, is not easy. Okay, so you got to give yourself plenty of time to actually experiment, and kind of get the program to work. I would say at this point of this class, the time that you spend to debug your program, for the lab/assignments, is actual study time. Simply because that is how you get familiarized with the concepts that we talk about in class. Um, so that's just my piece. Okay, that's just me, telling all of you, what is important, what you can do to understand the material better, so that you can get a good score, get a good score in the final exam. Um, all right, so Chris is typing. I'm gonna let Chris finish typing first, and then we'll go ahead and take a look at another sample program today, or we can go back to look at the one that we did before. All right, so any recommendation on best practices for debugging assembly code? All right, so I kind of illustrated that on Tuesday. Remember, at the end of the day, my program did not work, right? Um, so it's really kind of important. I think it's important, okay, to kind of review, how I debugged my own program. Um, because, first of all, what tool do we have for debugging that program? Let me go back to the spreadsheet. You guys can go there. I mean, someone is there already. Excellent. Okay, so Kevin, good job. Okay, being there, to from the get-go, that's good. That is good. So the analysis tab is very, very useful for debugging a program, because it shows you everything about the execution of the program. Every time we execute an instruction, the opcode or the address of the opcode will appear in column A. Every time we read a RAM location, it is reflected in column B. Every time we write to a RAM location, it is reflected in column C. And every time we change a register, it is reflected in column D. And everything we change the flags register, it is reflected in column E. So I think this is why, some of you may actually start to realize it's like, oh, so for that homework assignment where we have to substitute JXI with the 5 variations of conditional branches, if we did it using this mechanism, using this tool, that would have been like super duper easy, right? Because all you have to do is to basically just look at column A and just count the number of times that column A has the address of the no op instruction that you're supposed to keep an eye on. So that was actually me trying to get you guys to use the tool, because it's one application of the tool. Except for that specific program, you can also do it more or less, using just the Logisim GUI mode of logging, because all you really care about is just the program counter. But this tool, will give you the program counter. It will give you RAM read operations, RAM write operations, register changes, as well as changes to the flags register. So that is one part of my recommendation to Chris, is to use this tool. Now, to use this tool and you do not want to install River Spider, you can still do it. I mean, I have been doing that for years before I finally gave up and go like, okay, this is too much work and I need a challenge. I need a programming, slash, just finding a way to get around the problem kind of challenge. So that's really recent, because you can do all of this without using River Spider. You do need to run Logisim on the command line, because that's how you capture the trace. But once you capture the trace, you can basically hand import it into trace raw data. And then analysis, the script in this assembler, it will still respond to it, and it will still kind of give you, what you see here, except, it's just going to be a little bit more spaced out, because it doesn't trim the empty lines as well as what my script would do. Okay, so the other thing about debugging a program is you really need to know what your program should be doing. And I'm not only talking about the logic in C and C++, I'm talking more about how the stack should be used. In other words, how do we push things on the stack? How do we pop things from the stack? How do we get to items on the stack? All of those things you need to be very familiar and comfortable with, before you can debug your program, because otherwise you cannot really just look at the trace here and find out whether it is accessing the right location, or whether the stack pointer is correct or not, or whether you push something correctly on the stack or not. So it's very important to understand the agreement between the caller and the function that is being called, because that's for the most part our focus for the past few classes. Starting today, we're going to shift gear to talk about structures and other things. But if you guys need a little bit more time to talk about how the stack is going to be used, I can give you guys a few pointers of where you can go to learn all that stuff, because we have talked about all of that already. I gave you guys some programs, right? And what you need to do is to document those programs and understand what is going on with every single instruction. So you would go through what I would call a static analysis to kind of go through the program, comment every single line and say, okay, this line is doing this line is doing this line is doing this. After this line, this register has this. After this line, this register has this, and so on. So after the static analysis, then you go through the trace and you can comment, because if you make a copy of the trace, you can actually comment, using, say, column F, right? So you can just comment and say, okay, this is doing blah blah blah. I can give you an example. So let me give you a concrete example here. So right here, register D got changed to E0. Why is it changed to D0? So it's changed to D0 because, D is changed to E0 because we are reserving 32 bytes for the local variables. And that's why we are decrementing the stack pointer, not by 1, but by 32 at a time, so that we can allocate 32 bytes for buffer as a local variable. Alright, so next question from Chris is, would it be helpful to write some pseudocode about what the stack is doing before writing the code? I would just say that, as you write your code, comment your code, or, have one section of comment, to basically describe what the next few lines are trying to do, and try to express those in terms of stack operations, in terms of relating those assembly code to what the C code is trying to do. So I think that is probably very important as well. All right. Any other questions? We do have a lab tonight, so we do have a lab, and this one is just a lab. There's no code that you have to write in the long run, so it's just something that you can do in about, I would say, about an hour and a half or something like that at the most. But that's for tonight, okay? And this lab may actually help you with writing the swap subroutine, which is due next Tuesday. So I would definitely spend some time and just be patient to read through and try to understand everything about tonight's lab, because it is actually going to help you with the program that you need to write. Alrighty. So do we have any additional questions before we move on and talk about structures now? So we are moving on to talk about structures. I'm not abandoning the concepts that we have already talked about, because what we are going to talk about now is really stacking on top of what we have already talked about, no pun intended. And as you can probably imagine, getting all the material kind of understood and cleared, as soon as possible is really important now, because, if someone is not understanding, what is the stack, or what is a stack pointer, or how do we push, or what is a pop at this point of time, all of this material is going to be very, very difficult to absorb. All right. So, I'm not seeing any questions in the text channel, so we're going to move forward to talk about some new topic, which are structures. And this is one of the more difficult part of the class. Is I really don't know, how other people teach CISP360. I taught it a few times, and I definitely go over the topics that I felt was really important. But it's kind of hard to make the assumption, how other people would be teaching that class. Alright, so we're going to take a look at a very simple program that has structures in it, and then we're going to do some experiments with this program in C and C++, and then we'll trying to get an understanding of what is happening, like what is a structure, how do we access the members inside the structure, how do we make a variable that is a structure, how do we extract the address of a structure, because that's basically becoming a pointer to a structure. And then how do we change members that is part of a structure that is pointed to by a pointer. All right, so those are the things that we're going to go over today. We will be reusing some of the concepts that we have talked about already. So calling and returning from a subroutine, that's going to be in today's lecture, because it's impossible to avoid that. Passing parameters, definitely going to be in today's lecture. Local variables is going to be in today's lecture as well. So we are revisiting a lot of the concepts that we have already talked about. It's just that we are adding on top of all of that the concept of a structure. So we'll go ahead and take a look at a program that I'm just going to call struct.c. This program is not particularly interesting, other than it is a demonstration of what a structure is. Okay, so I'm still including standard integer.h. This way I have control over the width of integer types that I'm going to use. So this is how you define the structure. You say struct, and if you want the structure itself to be, if you want to use the definition of the structure throughout your program, you need to give it a name. So the name of the structure, or I should say a structure, is very similar to a class. Okay, it's basically a class that has everything by default being public, and you cannot have methods within a struct where you can have functions within a class and they're called methods. So other than that, hey, it's not really that different compared to a class. And also syntactically, after a struct definition, you need to have a semicolon, whereas after a class definition, you do not put a semicolon after that. But other than that, just kind of minor changes of syntax and whatnot. But in terms of the meaning, they're about the same. Okay, so you basically specify the type of a member. We'll call this member I. Okay, and then you can have other members as well. So this is signed. So we have J, and if you want, you can also have an array. We'll have K being an array of 8 characters. So we'll just say buff length, because using a literal constant, to specify the width or the number of bytes or number of elements within an array is kind of frowned upon. So we'll go ahead and say pound define buff length as 8 over here. All right. So do we have any questions about the definition of a structure, which is from line 5 to line 10? So this is more or less just a conceptual kind of thing, because we are not even getting into, how the members are being used. We're just defining a structure at this point. All right, I'm not seeing any questions. All right, so I'm going to start with main first, okay, because, in order to demonstrate, how to use a structure, I probably need to have a variable that is of the type of a structure. So I'm going to say struct x and give the variable a name. I'll call it v, okay, v for variable. So we'll just go ahead and just write a program exactly like this for the time being. And you're absolutely right. I did not do a single thing with the variable v, which is a local variable of main. I did not do a single thing with any of the members of the structure that v is an instance of. But I think this is a good time to really kind of look into the assembly code. So I'm going to do a v split. So this way I can use the right hand side to look at the assembly code. So we'll go ahead and edit struct.ttpasm. So this way we have a side-by-side comparison. All right, so first thing first, buff length needs to be defined, and the way we are going to define buff length. Oh, okay, I just type I forgot that I was not in insert mode and I started typing. So buff length is basically a label. A label in TTPSM and also in most assembler is nothing more than just a symbolic name where it has a particular value. So if you leave it blank, then it's going to be the current address, for the assembler. If you give it a specific number or a specific expression, it's just going to be defined to whatever the expression is. So this line is telling the assembler and say every time you see buff length, it's basically just substituted with 8. That's all it is telling the assembler. All right, so we got that. And now how do we define the structure in assembly code? As it turns out, there's no way to do it. Okay, there's simply there's no such concept of a structure in assembly language programming. And I don't really care about which assembly language you're talking about. You can be using a Motorola assembler. You can be using an Intel assembler. You can be using an ARM assembler. None of them is going to understand what a structure is. So now the question is, how are we going to define a structure here? So I'm going to leave a note here and say to do define struct x here. All right. So having that, I'm going to do a no op jmpi to main, and then here is main. And right here, I'm going to initialize the stack pointer before we get to main, because technically speaking, main is kind of like a subroutine, so it is not its job to initialize the stack pointer. So someone should have initialized the stack pointer before we get to main. Now main is special in this case because it doesn't have a place to return to, and as a result, it would simply have a halt instruction right at the end. And now the question is, what are we going to do to allocate for local variable v? So once again, we have to do how do we allocate for local variable v? So now I have a few places to insert additional code, but right now I'm just gonna say, okay, so let's go back to the C program and see if we can find some clue as to how to define v and how to define the structure itself. Okay, so we're gonna go through some exploration with the C program here. All right, so with this particular C program, the first thing I want to do is to find out where's the address of v. Okay, so I'm going to define two more local variables just so that I can have an idea of where things are. Okay, so we'll have one a-bit unsigned integer that's defined before v. I'll call this one a, and we'll define another one called b over here. And in order for the compiler not to optimize everything out, I kind of need to force it to say, yes, everything is still important here. Do not optimize them out. So line 18 is not really something that I want to do, but if I don't have line 18, the compiler will basically say, hey, you're declaring all of these local variables and you're not using them, so I'm going to take them all out. Okay, and that's what the compiler would do. I have not found a way to turn off that optimization feature of the compiler. So I kind of need to do this in order to have A, B, and V continuing to exist, even though I don't really care about where. I only care about where they are, but I'm not using them for anything useful in this case. All right, so gcc-g, which enables debugging, and then -o to specify the name of the executable, and then struct.c, which is the name of the source file. And it compiled just fine, and then we use gdb struct, and here we have the program. And I'm going to put a breakpoint on line 18, so when I run the program, it's going to stop on line 18 right here. So you guys are going to ask or wonder, what can I possibly be looking at this point? Because the initialization of A, B, as well as one member of V has not even happened yet. Okay, what can I possibly be looking at this point? I'm looking at the addresses. Okay, so I'm going to say print the address of A, print the address of B, and print the address of V. Alright, so we're going to take a look at this. You can ignore most of the digits except for the last two digits if you want. So we can now see that the compiler actually does a pretty good job optimizing. You can see how A has a lower address compared to B, and we can also see how V has the let's see, yeah, V actually has the lowest address. So V has the lowest address, and then we have A, and then we have B. Okay, so that's one thing we can see. We can also do something else. We can also show the size of, which is the number of bytes a variable is going to take up. A is going to take up a byte. Okay, that seems to make sense. B is going to take up a byte. Seems to make sense. And V is going to take up 10 bytes, which also makes sense, right? Because it has two members that are 1 byte wide, and then it has an array that has 8 1 byte wide elements. So it kind of adds up to a total of 10. Okay, so that's kind of interesting. Now we want to look into V and find out, the relative positioning of its members. If I remember correctly, it has a v.i as a member, so I don't care about the value. I only want to know the address. So v.i is there, and note, the beginning, the address of I, member I of V is the address of V itself. Okay, so kind of take note and remember that. And then we have J. J is 1 byte after I. And then K, which is the array of 10 bytes, or 8 bytes, sorry, is right after that. So when you just look at the last digit of the addresses, the first member has a 4. The second member has a 5, which is 1 plus the address of the first member. And then the third member has a 6, which is the address of the second member plus the size of the second member. All right. And just to complete this exercise, we can also just look at v.i. The member I has 1 byte, the member J has 1 byte, and then the member K has 8 bytes. There we go. So another kind of interesting point. Okay, it's probably not interesting, but it's worth noting. Is the size of V is basically the sizes of its members all added up, because 10 is 1 plus 1 plus 8. All right. The \377 and the \177 are octal numbers. So 377 is basically all ones. Because as an octal number, each digit is occupying 3 bits. So we have the 7 and the 7, being all ones for bit 0 to bit 5, and then the 3 are 2 ones, and that would be bit 6 and bit 7. So we have basically 8 bits of ones for the first byte of where at that location. And the reason why it displayed both of those is because I was asking for the address of a byte. But remember, a pointer or an address of a byte can also be seen as an array. And the debugger is smart enough to say, hey, you are looking at the address of a byte, which is a character. Let me try to interpret it as a string for you. That's why you see the double quotes. So the first byte, or the byte where v.i is located, is basically FF in hexadecimal. The next byte is 7F in hexadecimal. And then the byte after that is a null terminator. And that's why you see the string is terminating right here, is because whatever byte is after v.j is a null terminator. All right, cool. All right, so all of these experiments is important because it is showing us internally how things are organized. Okay, so now we're going to get out of the debugger, and then we're going to go back to edit our code. So we'll go ahead. I cannot remember whether it's a dash lowercase o or uppercase O that will kind of split it vertically. So I am going to give this a try. Nope, wrong one. It's the uppercase O that will split it, side by side. which is what I want. Okay. So this gives me an idea. Okay, in order to define the structure of x, I'm going to do something like this. I'm going to say x, as a prefix, and then xi, and xi is basically a label to tell us where we can find member I. If I give you the address of an entire struct x, what is the offset from the address of the entire structure to find I? And you guys might remember, the address of I and the address of V, oh, excuse me, let me take that back. The address of V.I and the address of V are the same. So the first member is actually at the very beginning of the entire structure, in terms of memory. So it has an offset of 0. So I'll just kind of write down here, offset from beginning of structure to member I. The next one is x underscore j. I would use 1, okay? I would use 1 if I want to save time and so on. But my job here is not to save time. My job here is to explain things to you guys. So I'm going to use another format here, which is x underscore I 1 plus. And can someone explain to me why I would use this format? And this is going to be buff length plus. There we go. Nope, this is wrong. Okay, never mind. It's 1 plus here. And then x underscore size, that is going to be x underscore k buff length plus. There we go. Alright, so getting back to the text channel, you don't have to remember the size of every variable. Exactly. So if I want to insert things and change things around a little bit, the way I'm defining the offset to j and the offset to k is only relative to what is before that, the member that's right before the member that I'm trying to define, or the offset of the member that I want to define, and the size of that member. And anything before that does not matter, right? So by doing it like this, okay, if I need to, change the ordering, or if I need to insert a new member and whatnot, the changes that I need to make to these definitions is going to be very limited. All right, let's check out x underscore size. Okay, that's a special label because size is not really a member of a struct x. So x underscore size is actually trying to tell us how many bytes is one struct x. That is what it is trying to tell us. So right now, if you just kind of follow the definition of the labels, x underscore I is a 0. So x underscore j is basically 0, 1 plus, which is 1. And then x underscore k is 1, 1 plus, which is 2. And then x underscore size is going to be 2, 8 plus, which is 10. In other words, I'm using label definitions to help me understand where I can find a member inside a structure by defining just the offset from the beginning of a structure to a member. That is how a structure is going to be, quote unquote, represented in assembly code. So it's all manual work. Okay, there's nothing, well, I shouldn't say nothing. There is a way to sort of automatically generate all of these offset here, but it requires the use of a compiler, and there's no, as far as I know, no one has written a backend to GCC to crank out TTP ASM code, so that option is obviously not available. So let me just kind of pause and see if there are questions related to line 4 to line 7 and how those specific lines are used to define the structure. In other words, in assembly code, line 4 to line 7 is equivalent to what line 5 to line 10 are trying to do in the C code. So I'll give you guys a few moments here to kind of try to absorb this and ask questions. All right, there are no questions. Oh, one more reminder, since we'll be introducing new concepts and whatnot, even if you are not taking notes right now, it might be helpful, if you're just gonna jot down the time when I start to talk about a specific topic, like what I just did, right? How do I define a structure in assembly code? So that's kind of important. All right, so now we are moving on to the next to-do. This one is already handled, so I can now go back, delete the to-do, and now I have the next to-do, which is in main. So how do we allocate for V, which is a structure, an instance of a structure? You can look at it as an instance of a class, which is an object. All right, so what we want to do is to allocate for a local variable. And can someone remind me, where do local variables live? On the stack. Very good. Okay, so they're on the stack, which means I need to somehow reserve 10 bytes on the stack, right? In order to fit a struct X thing on it. Okay. All right. So I got a few options here, right? I can do something like this. I can say decrement D, and just repeat this 7 more times, right? So I'm gonna do a YY 7P, and there we go. This is why I like VI, okay? Because you can actually specify a repeat count and then specify what operation you want to perform, and it will just go ahead and do that. Oh, I take it wrong. Okay, this is wrong, because I need 10 bytes. There we go. Okay. It will do the trick, but this is not the best way to do it, is it? Because just like what I did, I forgot, okay, the actual length or the actual number of bytes of a struct X, and I did it wrong. Okay, so let's not do this. Okay, let's get rid of all this stuff here. We can just say line 14 to line 19, delete. There we go. All right, so what about using a subtract, right? We got a subtract instruction. Got to use that one at some point. So we'll do a LDIA with 10, and then we'll subtract A from D, which means D is now 10 bytes lower than where it was. So hence I have just reserved 10 bytes on the stack. That looks okay, but doesn't this kind of defeat the whole purpose of having labels that we defined earlier? All that stuff with X underscore as a prefix. Why would I do all that stuff when I don't use any one of those labels, right? So instead of using 10, what should I be using here? 10, this format is fine, okay? It's just that I don't want to use a literal number. X underscore size, very good. Okay, so Eric is correct. This is why I want to use labels, because this way I can reuse the labels. If I need to change anything, I just change the definition of the label, and I don't need to hunt down every single 10 within the program and ask, is this 10 referring to the size of a struct X? Is this 10 referring to the size of a struct X? Because 10 can be many things. Being the size of a struct X is just one of those things. So this is why I want to use symbolic names. Is I could have defined it wrong, but I only have to fix it once. That is the reason. Cool. Now, if I allocate at the beginning of a function, I probably should be deallocating it at the end of a function, okay? Because when whatever you allocate on the stack, you better make sure that you also deallocate it as well. So now, in between, now we have the storage, for the structure X. But tech, you got this wrong, because we also have two other local variables here. One is A and one is B. What are we going to do with those two? Okay, so this is where we need to have a picture of what the stack is going to look like. Now, the compiler does some optimization, rearranging things a little bit for reasons that I will not talk about, at least not at this point. But for us, we can just kind of say, well, we like, we like, local variable A to be at the lower address, and then we have V, and then we have B. So B is going to be the one at the highest address. Then we have V, which is going to take up 10 bytes, but it's going to be lower than B on the stack. And then finally, we have A, which is at the lowest point of the stack. Okay, so we'll just kind of go ahead and try to arrange the stack in that way. All right, so let's go ahead and do that. So what I'm going to do now is basically a map. Okay, you look at this as a very crude map of what is on the stack. So first of all, we have local variable b, and then the next 10 bytes we're going to have local variable v, and then we are going to have local variable a. And when all of this is allocated, the stack pointer should point to the last thing that we allocate on the stack. So is that part okay in terms of what I'm trying to draw on line 13 to line 15? Let me do something a little bit different here, just so that you guys can kind of visualize how local variables are defined. Now this part should not bother you too much with your homework, because in your homework you only have one single local variable in swap, so that should not be too big of a deal. Okay, Omer is typing, is there any reason for arranging it that way? Why not ABV? Um, Simply, it's just because we want to follow the order of the definitions. So whatever comes first has the lower address, and whatever is defined later has a higher address. And there's no specific reason to do that, other than we want to preserve that order, just so that I mean, you can just do it in a random way. I mean, you can say B and then A and then K and then V, or you can have V and then B and then A, and then you can have V and then A and then B. It doesn't really matter. There's no specification in C or C++ that specifies one way or another. So the compiler it's entirely up to the compiler to decide where it wants to allocate for a particular local variable relative to where all the other local variables are located. So that part is not spelled out. It's really just a matter of it's just easier to think of it this way. So okay, so I'm going to use a new spreadsheet here, just as a documentation feature. Okay, so it's not going to have any major important stuff in this one. So if you don't have access to it, which I don't think you do, it's not a big deal. Let me just kind of double check and see if it is already shared. Okay, I'll just call it stack use. And it is restricted, only people added can open this link, so it's not shared with anyone at this point. I can share that later on. So it's really just a means for me to kind of display what is coming on the stack. All right, so I'm going to use column B, to kind of indicate what is at a particular location. So remember, we want B to be at the highest address. Okay, I can do this in a reverse order. It's just that I have to I have to go back to this location here and say A is going to be the one at the lowest location, and then the next one up is going to be V. So V is going to take up 11 bytes. So I'm not really sure, is that 11 bytes to me? 10 bytes, sorry. So the next 10 bytes are V. But we can also kind of look into V and go like, oh, but we do know, what is in V. So v.I is here, and v.j is here, and v.k bracket 0 is here, v.k bracket 1, v.k bracket 2. I really should not have made the buffer this long because it's just a whole bunch of typing that doesn't really help with the understanding of how memory is used when you have a structure. So this is v.k6, and finally we have v.k7. There we go. All right, so with the three variables that we have in main, this is where we're gonna supposed to find A. This is where we are supposed to find V, which is a structure, and this is where we are supposed to find B. And someone's going to ask the question, it's like, okay, so where is this on the stack? Well, it kind of depends on whether main is being called by someone else and what the stack already has at this point. So all I know is when this is all done, when everything is allocated, the stack pointer D is going to be pointing to A, which is my local variable A, and then D plus 1 is going to be pointing to V.I, and then d plus 2 is going to be pointing to v dot j, etc., etc. And then over here we have register d plus what is it, 9, should be pointing at b. So everything is still relative to where the stack pointer is pointing to. The stack pointer right after the allocation of the local variables, the stack pointer should be pointing to the local variable that is at the lowest point, and then we have the next local variable, and then we have the next local variable. Is this part okay? Does everybody kind of understand, what this picture is trying to show you? All right, we have confirmation. Excellent. All right, so I'm not interested in knowing the absolute address of all of these components. Instead, I only want to know where I can find these things relative to where the stack pointer points to. So relative to where the stack pointer points to, A is at a relative position of 0 because it is right at where the stack pointer is pointing to. v.I is at 1 byte, from where the stack pointer is pointing to, and then B is at 9 bytes after, where the stack pointer points to. So those are the values that I want to define labels for, because this is how I want to be able to refer to my local variables as offset from where the stack pointer points to. So that's how I'm going to, this is why I'm going to define these labels in the assembly code. And let's see if I can, have to look at my phase 2 just to make sure that that's not overlapping with important stuff. Okay, so right here I'm going to say, main underscore A is going to be 0, because main underscore A is only representing the offset in number of bytes of where I can find local variable A relative to where the stack pointer is pointing to. And Christopher said, shouldn't B be offset by 11 bytes? Yes, you're right. I could not count because I kept thinking the V only has 8 bytes. So this is also going to be important because, okay, so remember this mistake that I made, okay? And this is not the first time that I thought the structure only has 8 bytes, okay? Because the array has 8 bytes, but it also has 2 other members, and each one is taking up 1 byte. And anyway, this is something that somehow was stuck in my mind. I kept thinking that the local variable v only has 8 bytes. So now I need to define where I can find v, sorry. And most of you are just going to look at this picture here and go like, oh, that's going to be 1. See, right here, it is 1. Okay, we can do that. And now we can specify where we can find B. And if Christopher did not correct me, I would have put down a 9 because that's what I thought I saw in the picture. This 9 is also incorrect because it's supposed to be 11 here. But I would have made a mistake here, okay, and put a 9 here, and that would be bad. That would have been wrong, okay? So how am I going to avoid making these really kind of stupid mistakes? But they're not easy to fix because it's not easy to find that problem to begin with. So how am I going to fix this problem, or try to minimize the chances that I can put down a literal number and turn out to be wrong? Has something to do with what we did earlier in class, right? We already kind of talked about that. All right, so we got Philip and Christopher both typing right now. Debug. No, we don't. Well, okay, we can debug it, but I would try to avoid having to debug it in the first place. So I could do the same thing that I did for the structure. Exactly. So I want to express everything, try to be as relative to the thing before that and the size of the thing before that as much as I can. Except here on line 16, 17, and 18, I'm no longer talking about where I can find members of a structure. I'm now trying to talk about where I can find local variables on the stack. But nonetheless, they're all still relative to where the stack pointer points to. So in a sense, I'm still dealing with offsets, okay? Okay, so if I'm dealing with offsets here, I'm going to say, well, since this is after A, it's going to be where I can find A, but add 1 byte after that, because that is the size or the number of bytes that local variable A is going to consume. So with this one here, it's going to be the local variable before B is V. Now I have to try to think about, okay, but what is the size of that thing? So what do you guys think? What should I type here to specify how many bytes are being used by local variable v? Exactly. Okay, so this would be bad, right? Because this is my mind playing tricks, thinking that the structure only has 8 bytes. No, 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 no. We don't do that, right? We want to use the label that we have already defined that would tell us the number of bytes in local variable v. So put a plus here. And last, we're going to have something that is sort of equivalent to x underscore size. We'll just call that local variable size, LVS. I'm too lazy to type the entire thing out, okay? Local variable size, or the number of bytes used by local variables. I'm just going to call it LVS, okay? So how do I compute this? Well, it's kind of the same thing as x underscore size. So this time I look at the very last local variable that I defined, which is v. And then we say, okay, but how big is a b? B as a local variable only takes a 1 byte, so we'll have a 1 plus here. So this is how I would define these label names relative to, so that I can access various things on the stack without having to keep in my own mind, oh, this is 0 byte away from where the stack pointer points to, this one is 1 byte away, and that thing is 11 bytes away. I don't want to have to remember any of that stuff. I want to be able to refer to those things by their symbolic names. So the idea of using symbolic names is really similar to why we have mnemonics, right? So instead of using the actual opcode of JMPI, which is I think 40 in hexadecimal, I mean, there are very few instructions in TTP, so it may be doable by memorizing all of the opcodes, but it's not even necessary, okay? Because the assembler is here to help us convert the mnemonics, which is a symbolic name of the opcode, into the actual opcode. And for the same reason, we define these labels. So are we doing okay so far? Are there any questions about what I have written in this program so far? All right, I'm not seeing any questions. Okay, cool. All right, so now on line 22, which is, we want to allocate not only for v anymore, so I'm going to change the sentence for local variables, okay? Because we have a, v, and b. They are all local variables to us. So how do we allocate for all of the local variables all at the same time? We know that x size is not going to cut it, because that's just the size of one of the local variables, not all of them. So what should I use here so that I can allocate for all of my local variables in one shot? Exactly. Okay, main LVS. Okay, that's the number of bytes that we need to allocate, and that would be the same number of bytes that we need to deallocate, which is here. There we go. Cool. Do we have any questions at this point? Okay, because right now all we have done is to implement the declaration of the local variables, and that's it, right? We allocate. We didn't do a single thing about the local variables, and then we quit the program. And before we quit the program, we also remember to deallocate the local variables. So are we good so far? because the next thing we're going to do is really to implement this assignment statement here, or the assignment expression. All right, all good, excellent. All right, so now we're going to implement this really super complicated assignment statement. So let's go ahead and do that. Okay, let's find out how we can do this. Um, Although not necessary, most of the time I personally would compute the right value of an assignment, which is the value that is being copied to the left hand side. That's usually what I do first. It's not 100% necessary to do it this way. Sometimes it actually makes sense to compute the left hand side, which is the address of whatever you want to store that thing to. Sometimes it makes sense to compute the left hand side first, or what we call the L value, instead of computing the R value first. Our R value is really easy to compute. It's just 0. So yeah, we have a few registers to play with. I think we're going to be okay if we just say, yeah, don't touch register A now because it is the R value. R is right hand side, so that's why we refer to the 0 on line 18 as the R value, because it is on the right hand side of an assignment. Alright, so now we need to compute the L value, which is the left hand side value of v.I. Now L value is kind of a misnomer, because it's not really a value, it is an address. Because the left hand side of an assignment needs to provide an address so that we can store the right hand side value to that particular address. So the question, it really boils down to, where can I find v.I in this case? So when you look at this picture here, someone's going to say, oh, this is where we can find v.I. It is 1 byte away from where the stack pointer points to. So that's easy to compute, because we can just, don't copy this. You might want to jot down bad practice on your notes and note the time, because I'm going to fix this. So one way to do this, after you see this map of the of where things are on the stack, you can now say, okay, let's just copy the stack pointer to register C, increment C, now C, increment C, and now C is the address of member I of local variable v. So now we can just do a stca, and that would accomplish this assignment here. This is a really, really, really bad idea. Okay, why? Could I? Oh, right. Sorry. Let me see. I'll just get rid of my own webcam so you guys cannot see my facial expression, and put it here. There we go. So now we can actually see, and I can even shrink the width of these columns. They don't need to be this wide. There we go. And switch back here, and now we get to see the map and also the code. Alright, so from the perspective of, is this code going to handle the local variables as they are allocated here? The answer is, yeah, it's going to do it. But is it a good idea? The answer is no. This is a terrible, terrible idea. Why? Because if I change how I allocate things on the stack, like if I say I need one more local variable before A, that's going to shift everything up, right? And this code is very sensitive to where I put things, so it's a bad idea. The other hint that this is a bad idea is, tag, why did you bother defining all of these labels if you're not using them, right? So both of those are pointing to the direction of maybe we should reconsider how we're going to do this, right? So let's go ahead and get rid of these 3 lines, and then we'll say, okay, so how are we going to do this? Well, before we can find the address of a member of a structure, we probably need to find the address of the structure itself, right? So we'll go ahead and find that first. Okay, so now we load B with the offset to the local variable v itself, not any one of its member. We just want to know where is the first byte of the entire local variable v. So this is the offset. We need to remember to add the stack pointer so that now B is the address of local variable v. But that's the address of an entire structure. Okay. Can someone tell me again what is the purpose of x underscore I? In other words, this label here, I'm not asking what it is defined to. I'm asking about what is the purpose. What is it representing? And it is the offset to member I. Okay, so if B right now has the address of the beginning of the entire structure, and x underscore I has the offset from the beginning of the structure to member I, what do I need to do to find the address of member I of local variable v? Exactly. Okay, so looks like we can just do something like this, right? Well, the syntax highlighter says no, not gonna do it, right? So that's because we have an immediate constant that we are trying to add to a register, and that doesn't happen. Okay, I cannot even remember how many times we have explained this, or how many times I have explained this. It's because there's no pathways to do this. Okay, the processor simply has no path to connect the output of RAM, which is the D port, to one of the inputs of the ALU, and the ALU is the only place where we can do a general addition. Okay, so we simply cannot do this. It's not a limitation of the syntax. It is a limitation of the processor architecture itself. All right, so oh man, that means we have to use another register, okay, like C, okay, LDIC with XI, and then we add register C to register B. Whew, okay, so after this, B would now be the address of v.i. And then someone is going to point out and say, Tech, this is really unnecessary, okay, because x underscore I is 0. So why don't we just kind of skip all of this stuff here, just kind of delete line 30 and 31, because neither is needed. Why shouldn't I do that? Why should I just leave the code as it is now, even though we are just adding 0 to b, which doesn't change the value of b at all? So why should I leave it here? I'm very tempted to hum the tune of Jeopardy. But I'm not a good hummer, nor am I a good singer, so I'm just not very musical when it comes to performance. So I'm not going to do that. Well, the reason why I don't want to do that is because what if somebody is trying to play a trick on me, and the C code, okay, let me switch back to the C code here, and they decided to do something like, whoops, nope, there we go. Go back here, there. They changed the structure by rearranging where I can find the members. So if that happened, and I decided to optimize my code because x underscore I was a 0, then this program is not going to work. That is why. Okay, so I'm going to undo the changes in the C code, and I'm just going to keep it here. And then someone else is going to say, but Tech, surely you can do something about this, okay? Because this code is it just doesn't seem necessary, okay? Because it looks like, when we, how should I put it? Okay, so on line 27, we know for sure that B is going to end up with a value of main underscore V. Then we're going to add the stack pointer to it, and then we're going to add x underscore I to it. So why don't we merge the two addition by adding with the constant on the LDI side, and avoid having one extra add instruction that executes in runtime, that's going to use up actual processing time. In other words, what I'm proposing is we can just go ahead and add the xi over here, and then forget about doing this because that is no longer needed. Well, as it turns out, this is permissible. This is actually fine. It's not a problem. Okay, Simply because there's no dereferencing whatsoever at this point. We know that both v main underscore v and x underscore I, they are just displacements, and one displacement is just going to be stacked up upon the other displacement. So there's no problem adding these two displacements in order to find what we need to find. And we just have to remember that it is still a displacement from where the stack pointer points to. So we still have to remember to add the value of register D to register B before we end up with the address of v dot I. So we'll do it this way, right? And then we do a stba. So that will handle storing the 0 into v dot I. And now we need to store into B. Now this part is going to be like kind of boring because we are just going to do the same thing over here. Okay, we find the offset of where we can find B from where the stack pointer points to. Add the stack pointer to the offset, stba. So that's going to store the 0 into local variable B this time. And then the A is like super duper easy, right? We just have to do the same thing again, except this time we use the label main.a, main underscore a, not dot. Add bd stba. All right. So at this point, we truly have the equivalent code to the C code. This code here is the same as this C code here. And I can claim this all day long until I actually run this program and show you why these two programs are equivalent. All I'm doing is just talk, right? So let's go ahead and run this code. Now there's one change I would like to make, which is to change the initialization to 0 to non-zero. So we'll change it to hexadecimal. Let me think. Just randomly, I'm just putting 3D here. Okay, that's just a random value that just popped up in my head. The reason why I'm doing this is because all the locations in RAM are pre-initialized to 0 already. So if this is what I'm doing, if everything is just re-initialized to 0, it may be difficult to see. So instead of doing that, I'm going to change it to 3D, and 3D in hexadecimal is what in decimal. So I want you guys to figure this out without using a calculator, okay? Because if you understand the how a value is represented by a certain number in a certain base, this is not difficult math. I mean, it's one multiplication followed by an addition. So, and you don't even have to do the math. Okay, that's the nice thing, is you don't even have to do the math, because we can use postfix notation where we expect to find an immediate value. 61. All right, you guys are so close. No, 61 is the correct answer, but I'm talking about how can I do this without having to go through the mental math? How can I use an expression to do this calculation so that I don't risk my puny brain making a mistake in the calculations? And you can see that I have already made quite a few stupid mistakes tonight. So I don't want to risk any more. All right, so let me show you. I'm gonna wait until Max is done. Go ahead, Max. I'm gonna wait. Cool. All right. Almost there. I think Max's answer is going to deserve 3.9 over 4, because it's just this much off from the actual correct answer. All right, so we'll go ahead and take a look. So we have 316 multiply, because the 3 here is representing the number of 16s that we have, because this is a hexadecimal number. Hexa is 6, deci is 10, so hexadeci is base 16. So that's why the 3 is representing the number of 16s. And then after we take care of the most significant digit, now we have to figure out what D is representing. D is representing 13. So that's why Max is gonna have 1.1 taken off from the 4 out of that scale. Sorry about that. All right, but we need one extra plus here because otherwise we are not adding the 13 to the product of 3 times 16. So for those of you who typed 61, you were absolutely correct. Okay, it is 61, but I'm just spelling out how to do how to convert the hexadecimal number here into its value, so that this way I don't have to even carry out that mental math. 3 times 16 is 48. 48 plus 13 is 61. So anyway, all right, so let's check out this program, right? Let's find out whether this program is going to do what it is supposed to do. So we'll go ahead and exit all. Okay, XA, exit all. And that means the C code is updated, and so is the assembly code. Well, let's run the C code first, okay? Because some of you may say, but Tech, we don't even know whether the C code is going to do what it is supposed to do. So let's check it out first. So now we say gdb struct like that. Put a breakpoint on line 19 this time because I want to know whether A, B, and the first member of V are indeed changed to 61. Run the program. Now that it has finished the assignment, we say print A, 61, cool. Print B, 61, cool. Print V.I, also 61, cool. Nice. And before someone asks, but why is it, putting quote equal quote here? I know some of you are asking that question, which is natural. Okay, your curiosity is a good thing. But this may be something that we can answer already based on what we have already talked about in this class. Because when the debugger finds that I want to print the value of something that is only 1 byte wide, it will naturally think, oh, that's a char. So that's what it's doing. It's interpreting 61 as an ASCII code, and that turned out to be the ASCII code of the equal symbol in the ASCII table. So there you go. All right, so getting out of the debugger, now we want to test run this code in TTP, the text toy processor. So I'm gonna do it over here. So I'm going to copy the source code over there. It's in the file right now, so I need to do an xclip-cell clip redirect from the name of the file. All right. You can look at this as a command line way of doing copy and paste. Well, copy into a clipboard, and then I can paste it in the browser. All right, so paste right there. And we're going to make sure that we don't have any errors. It's going to have some errors because the previous program was longer and is still lingering around. So we're going to remove the unnecessary part. Just kind of get rid of that first. And then we give the assembler a little bit of time. No errors. Okay, so don't make a copy yet, okay, because we haven't run it yet. So right now we have the code, and I will do this one more time, just doing it manually. So you might want to jot down the time if you want to kind of give yourself a reminder of how to run a program manually, and still be able to capture the trace, okay? Because I'm gonna do it right now. All right. So the way we do it is to download the RAM file. So you go to the RAM file tab, go to File, go to Download, right there. And I use the CSV, even though you can use the TSV. I stick with the CSV. And my browser is set up to ask me about where and also the name of the file. So I'm going to call this struct.csv and save the file. So now the file is saved. And then I switch to the command line. And this is going to be a longer command. So I'm going to spell out the entire command here. java-jar, and then we have to tell it where to find logicsim.jar itself. logicsim310.jar. And then we have to tell it where to find processor 0004.circ, because that's the file that the logicsim is going to take on. Okay, so don't remind me. I think I can remember to do this because we have simulation on top of simulation, and the command line shows. So I'll tell you what I mean by that in just a moment. So documents CISP310 river spider and then processor 0004.circ. Okay, so if I were to just press the enter key now, it's going to run Logisim and it will load processor 0004, which is TTP, into Logisim. So that's not what I want to do because I want to run this program on the command line so we can capture the trace. So the next thing we need to do is to say -load because we need to specify where are we going to get the content of RAM when we are running this on the command line, because there won't be a chance for you to right click on the RAM component to say load image from here. So we have to use the command line to specify where that RAM content is coming from. So that's going to be coming from temp slash, what was it again, struct.csv. Then if I press the enter key right now, it's just going to be loading it and it will still be running in GUI mode, which is not what we want. So now we have to specify -tty, which is teletype, which means, okay, don't go into GUI mode, go into command line mode. And then we specify table. I think table is the only option for -tty. So, I don't even understand why it is here, but that's the only thing you have to specify -tty. So if I press the enter key right now, it's going to just spew out a bunch of stuff. Okay, but it's going to be on the screen, and it's very difficult to capture. It's not like impossible to capture. It's just more difficult than it needs to be. So I'm going to redirect it to a file, which is temp struct.tsv this time. So TSV is the abbreviation of tab separated value, which is actually descriptive of the format of that file that we are capturing right here. So we press the enter key. It's all done. And we'll take a quick look at the file that we just captured. And it looks like this. Looks kind of correct to me. Okay, so and then what we need to do is to go back to the tool that we have, and then we go to trace raw data, the tab, and then we go to file, and we go to import, and then we go to upload. And then we specify the file, or if you have your file manager open, you can just kind of just drag and drop. So the file that we want to use is struct.tsv. So remember, it's the tsv file that you want to upload, not the CSV, because that's the file that we downloaded. Okay, CSV is what we downloaded earlier. TSV is what we are going to upload. So we have to be careful here. Replace current sheet. Okay, that's what we want to do. We want to specify the separator as tab, and we want to turn off convert text to numbers, dates, and formulae, and then click on import data. All right, that's it. Okay, this is all you need to do to capture the trace and then upload it to the tool. And the tool is going to do the analysis using the analysis tab. And you can see it's still working. It's just kind of not nice because it has a lot of empty lines. But if you kind of ignore the empty lines, it's really the same thing as using River Spider itself. It's just that there are a few more steps that you need to perform here. All right, so next question is, Batak, you still haven't told us whether the program worked or not. That is correct. Okay, I did not tell you whether the program worked or not. So I think this kind of goes back to, oh wait, I promised you to explain one thing and I forgot about it. All right, so it's just kind of interesting because I want you to note this because just because how convoluted it is. Okay, the program that we want to run is actually contained in this file. Those are all the opcodes. Okay, they're all in hexadecimal and whatnot. But that opcode cannot run on the Intel processor, right? It only runs on text toy processor, and text toy processor, including the microcode, is specified in processor 0004.circ. But that's just a description of a circuit, right? It has a lot of components, right? It has a lot of registers, a lot of multiplexers, demultiplexers, and whatnot. But nonetheless, it cannot run by itself. So in order to run, in order to for the processor to work, it has to be emulated by using Logisim. So Logisim, we have been using Logisim since day one of this class, right? That's just a program, with a GUI mode, and you can just kind of design your circuit using AND gates, NOR gates, and whatnot, and it will just kind of go through all that stuff, and compute stuff for you. But that's a Java file, right? It's a jar file, which is a Java archive file. That J stands for Java, and then AR is archive. So that by itself cannot run natively using the Intel processor. So in return, you need Java to interpret the actual Java bytecode in the jar file. So we have just like 4 levels of indirection here to get this program to work. I just want to point this out because I find this slightly amusing. Anyway, right. So getting back to, I got distracted. I distracted myself again. All right. So getting back here. Okay. So now we want to know, how do we know whether the program worked or not, right? So at this point, everything, all of these numbers are relative to where the stack pointer is. So, okay, that doesn't seem to be helpful because we don't know at runtime what the stack pointer is pointing to. Except we should know, right? Because we know that this is the highest location in RAM, and this is, whatever number it's supposed to be. So this is location 255, and if I just say this is this number -1, I'm just too lazy to label everything by hand, right? So that means at location 244, we should find 61 here. We should find another 61 over here, and we should find another 61 over here at those specific locations of RAM. And someone's going to say, but Tech, I am not going to convert all of these base 10 numbers into hexadecimal by hand. I'm not going to do it. That's fine. I'm not going to do it either. So I'm going to do a dec to hex conversion. And voila. Now we got the locations. Cool, isn't it? Huh? So now we know F4, F5 at those locations and FF at those specific locations. We should find the content of that's going to be representing 61, which is 3D. Okay, are we still doing okay so far? Have I lost anyone yet? I hope not. I mean, that was not the intention. All right. Oh, it's good. Excellent. Excellent. So now we go back to the other spreadsheet with the trays. And then we highlight column C because everything that we need to find is going to be in column C because we need to look for the overwriting of those 3 locations. And then we go to, you can use the menu. You can also just use the shortcut key if you want to. It's find and replace, Control H. So now we say we want to find asterisk. What was it again? F4, right? So F4 was one of them. Okay, how about this? We're going to use regular expression because I'm not doing this to teach you guys how to use regular expression. I'm doing this because it's too much trouble not to use regular expression in this case. So you don't have to learn regular expression if you don't want to. I'm not going to test you in the final exam using whether you understand regular expression or not, but it is very useful. All right, so we need to specify search using regular expression, and it automatically turns on matched case, which is fine. And what we need to find is going to be an asterisk character followed by the letter F in uppercase. because I think all the hexadecimal numbers are in uppercase. And this time I know exactly the three locations that I want. One is 4, one is 5, and the other one is F here. And then followed by a single equal symbol. Oh, I'm not sure whether equal needs to be escaped or not. Well, we'll give it a try and then we'll find out. And then after that, it's going to be a hexadecimal digit. In fact, we know exactly what it's supposed to be after that. It's supposed to be 3D. Right there. Okay, so this is the pattern that we're trying to find. We're looking for something that starts with an asterisk, and then an F, and then 4, 5, or F, and then an equal symbol, and then 3D. The only part I'm not really sure is whether it will look at this equal as a quantifier or not, because equal can be used as a quantifier in regular expression. So we'll go ahead and find. There we go. All right, so it does work out. Nice. So the first thing that is changed is F5, which is v.i. And then the next thing it finds is FF, which is our, what was it? FF is B, yes. And then it will, and then the last one is F4, which is A. And I think that is the order in the C code. Let me just double check. So lowercase, uppercase for splitting side by side. We want to look at struct.c and struct.ttpasm. All right, so the order is indeed the first thing we change is v.i, and then we change b, and then we change a. So the program does work out. Now this is important because there was a question earlier at the beginning of the class is, how do we know whether the program is working or not? This is how I check whether the program is working or not, is by me trying to figure out what location should be changed to what. And then I go to the trace to confirm whether those locations are changed the way they're supposed to be changed or not. And then there are usually a few things, like do we know whether the stack pointer is balanced or not? It started off as 0. Did it end with 0? The answer is yes, it did end with a 0. And then one last thing, it is actually kind of important. Because if your program misbehaves, it is possible for it to land on a spot where it would execute a undefined opcode, but any undefined opcode is actually behaves exactly like a halt instruction. So we kind of need to make sure that location 19 does correspond to the halt instruction as intended in the program. So we need to go to the Assemble tab, go to the very end, and look up the halt instruction. And just make sure that it is at location 19 in hexadecimal, and it does. So that kind of concludes my kind of more or less superficial checking of whether the program is working correctly or not. That being said, the source code is here already. I highly recommend you guys to make a copy of the entire assembler at this point, because we got the source code, we got the trace, we got everything in it already, right? But what you can do is to comment on these lines here. Okay, I sprinkled a few lines of comments, okay, as I explain things, but you probably want to put in your own comment into this code, because you want to use your own words to explain what is going on. In other words, don't just listen to my lecture and then use my own word and just kind of transcribe it onto your notes. Okay, so you're not going to do the job of the YouTube closed captioning software. Okay, that's what closed captioning is it converts my words, spoken words into written words. So what you want to do is to understand it first. Okay, understand it, have your own understanding, and then use your own words to describe it. Okay, because that's studying. I mean, that really is studying for this class, is just going through these programs, and just kind of comment it line by line, making sure that you understand all of the concepts and all of the rationale behind why I am doing it this way. Right. So I think this is all we have time for, and this should help prepare you for tonight's lab. So let me go ahead and release the lab for tonight first, and then I'll go, get something to eat, and be back in about 10 minutes. All right. This one is, where is it located? Call frame. There we go. And it does have a access code. Let me double check all of these settings. I am going to let you guys see the answers, because it is studying material. All the labs are actually intended as study material as well, because they do explain things in addition to just kind of giving you something to do. So it's going to be show at 9:50 p.m. And I just need to make sure that it understands it's tonight's 9:50 p.m. I'm not sure. I cannot tell whether it understands that part or not. The access code is framed. We can figure that out. Give me a second here. Let me finish this first so that some people can get started, and then I'll answer the question of how many classes do we have left. I actually have to look at the calendar to find out, but we'll find out for sure. Let's see. Yeah, Canvas doesn't really show me what it thinks this time is, unless I unless I go back and start to change it again. Then it shows me yes, it thinks it's tonight's 9:50 p.m. I don't like Canvas. All right, so let me click save and publish. There we go. All right, so let's take a look at the calendar and also the final exam schedule. So the first thing we need to do is to find the final exam schedule. So we just look up American River College final exam schedule. I am spoiled. I mean, I don't know what I'm going to do without Google. And I'm old enough that everything was printed on paper when I was in college. Okay. That's not what I intended to do. Let's see. Oh, come on. Scroll. There we go. Evening classes. All right, so the 12th is the first day of final exams, which means the 10th is the last day that we have lecture. And then on top of that, we want to find out what the exact time is. This class is a Tuesday, Thursday class, and the start time is 5:30, which is between 4:30 and 5:55. So that means our exam date is May 17th, and the time is 5:45 to 7:45. So unless I make a mistake, which is not going to be the first one today, that would be the date and time. So now, if I go back to the calendar, where's the calendar thing? There we go. View calendar. All right, so Omer has already gone through all the calculations. All right. So it's the end of April already. So we're going to look into May. So we got the 3rd. We got Thursday. So we got 1, 2, 3. So we got 3 classes. And the 12th is the first day of final exams. So that means we have 2 more classes to introduce material, because I need 1 class to kind of go over, last semester's final exam. I'm not going to call it the practice final, okay? I will stop and refrain myself from saying this is the practice final. I will simply say it is the final exam from the last semester, okay? So I'm going to use the 10th to talk about the exam from last semester. So that will leave us with only the 3rd and the 5th, basically next week, to introduce additional material. So does that answer the question? All right. Okay, so it's actually 3 plus the final exam, not 4 plus the final. So we are really kind of close, getting close to the final exam week. Yep, yep. This is what I would call a mad dash to the finish line. So I hope you guys are, getting the practice, getting the study skills down. You're getting all the good habits of studying. Um, and the tutor is available. The Beacon tutor is going to be a good resource. You guys are really lucky. I mean, we don't always get a Beacon tutor for this class, so you guys are kind of lucky that we have a volunteer. Jonathan volunteered to become a Beacon tutor. I mean, he's paid, but not really that much. All right, so he's paid, but not that much, to do his tutoring here. So use this resource. Okay, the tutor is a very good resource because he can try to explain things in a slightly different way compared to how I explain it, and he does understand everything too. So that's a good thing too. Alrighty, so I'm going to get off of the voice channel and the screen share unless there are questions that you want me to address right now. Otherwise, I'm gonna get off from screen share. I'm staring at the text channel, to see if there's any traffic. Doesn't look like it. All right, so I'm gonna get off from the voice channel, and you guys have a nice weekend. Um, I'll see you guys on next Tuesday. But all of this material here, you need to spend some time to try to absorb all of this material because there's a lot of stuff. Okay, it's just that you need to really kind of spend the time and really dig into it. Okay, find out all the what, how, and why as you go through the material. All right, so I'm gonna get off from screen share